Welcome to unit number 5, Ubiquitous Clouds and the Internet of Things. We'll look into cloud trends in supporting ubiquitous computing, performance of distributed systems, and the cloud enabling technologies like RFID, sensor networks, Zigbee, GPS for Internet of the Things. We'll look some innovative applications like smart buildings, smart power grid, retailing, and supply chain management, cyber physical systems for Internet of Things. We'll look into online, social, and professional networking as well. In cloud trends, we will see that how the distributed computing system basically have evolved as a clustered system, and from the cluster systems, it has moved to the grid systems, and from the grid systems it has become a peer-to-peer networking systems, and from peer-to-peer networking systems it has evolved as a computing cloud systems, or you can consider it a cloud computing environment, cloud computing system. So this is basically a trend that cluster systems appeared first in 1990, then grid systems appeared in 2000 and became very popular, but due to their lack of flexibility in general purpose of application, they are not being become so popular compared to the cluster systems. In 2005, many P2P system networks have appeared as file sharing networks and online social networks. Examples like ebook, video streaming, movie downloads, and social networking largely dominated the internet traffic. Computing clouds or the data center resources did not appear until 2007. Clouds are still in their infancy stage, even though all the underlying technologies are there. Still, clouds do reflect the latest development trend that emphasizes elasticity and flexibility by scaling out of computing services to automated data centers through virtualization. Few examples of the clouds for high performance computing or HTC, high throughput computing, and ubiquitous computing. One of the example is that IBM Blue Cloud system. A user basically uses an application server. The application server uses all uh, physical servers which are actually being virtualized by using Zen virtualization layer, Zen hypervisor. You can consider it as a hypervisor. As you already know, in previous units we have seen what is Zen is. Zen is a hypervisor basically. Okay, so we will basically as the user uses an application server basically needs the resources which are virtualized by using Zen virtualization layer, and there are some monitoring and the provisioning managers. In IBM it is known as a Tivoli. So Tivoli monitoring and provisioning managers is available for the for provisioning the virtual machines and monitoring them. Then we have Tivoli monitoring manager agent as well, which will see like what are the for each physical server we have open source Linux with Zen virtualization layer and Tivoli monitoring agent, which will look after the resources available on that physical server. So this is the architecture of Blue Cloud system built with the IBM hardware and software along with some open source Linux and Zen. There are some use of clouds for HPC or HTC and ubiquitous computing. So there are some IT companies which provides cloud services or products. Amazon is one of the major cloud service provider. Another is Anomaly, then Google, then GoGrid, Microsoft, NetSuite, Rackspace, and Salesforce.com. So these are the major cloud. Their major cloud offerings are different services, 6 infrastructure as a service systems, including EC2 for cloud computing capacity and S3 for on-demand storage capacity by Amazon. Around 10,000 businesses and individual users, including the New York Times, the Washington Post, and LLE. These are the major user groups. Likewise, for Google, for Microsoft, for Rackspace, and the Salesforce, you can see the various major cloud offerings and the major user groups. Same way, there are large-scale private clouds are being developed at NASA and the CERN. In 2010, two large-scale private clouds were under construction in the United States and European Union. The US cloud, which is called as Nebula, is developed by NASA and is designed for NASA scientists to run climate models on remote systems provided by NASA. This can save thousands of NASA users from acquiring supercomputers at their local sites. It also enables NASA to build the complex weather models around its data centers, which is more cost effective. The EU cloud is built by CERN in Geneva. This is a large private cloud for distributing data, applications, and computing resources to thousands of scientists around the world. CERN deals with large data sets and throughput with a global workforce and a finite budget. Many private clouds are also under development by the IT industry, large enterprises, and other government agencies. So, these large scale private clouds first are being developed with restricted access to specific user groups. Once these clouds become mature and more secure, then they are being actually converted to public clouds to use for use to the general public in the future. NASA's Nebula Cloud is a cloud computing pilot project under the development at NASA Ames Research Center. It integrates a set of open source components into a seamless self-service platform, providing high capacity computing, storage, and network connectivity using a virtualized, scalable approach to achieve cost and energy efficiencies. Nebula is currently being used for education and public outreach, for collaboration and public input, and for mission support. Nebula enhances NASA's ability to collaborate with external scientists and researchers by providing high-speed data connections and consistent tool sets and open data APIs used by commercial cloud providers. Built from the ground up around principles of transparency, Nebula is also an open source project. Each component of the Nebula platform will be available individually, serving SaaS, PaaS, and IaaS needs across the agency. NASA will use, or currently now this is older story, NASA is using the Nebula for mission support, education, and public outreach, and to encourage collaboration and public input. Basically, this Nebula uses a containerized data center to house servers on the NASA Ames Research Center campus. These containerized centers are proven to be the greenest form of data center because they are denser and thus require less energy to keep them cool. If you see over here, there are many different open source components which are being used by the NASA for development of the Nebula cloud. Basically, you have Nebula over here, physical machines are there on which Nebula is being installed. You have Lustre file system, then you have virtualized server. Ubiquitous is being used for the virtualization. It will act as a VM controller. Then we have message queuing system through which like all the virtual machines are actually being the messages related to the virtual machines are being managed by the RabbitMQ messaging queuing system. And Solar indexing by Apache Solar indexing and the search is being being used, which is being developed by the Apache, is being used over here. We have fabric based deployment and we have Selenium grid and cruise control. These are the two different deployments which are being used for the Nebula web services, Nebula services. Uh, they have different services, software as a services based on the which is being supported by Python and the Java, and there are many other cloud web interfaces which are being mentioned over here, through which you can directly access the message queuing system, you can access their file system, you can access the virtualization layer, and we have authentication and uh, we have authentication layer over here as well. Okay, so this is a basically Nebula cloud by the NASA, which is already being developed and available at nebula.nasa.com or nasa.gov. Then we have a development by Sun, which has long been an influential leader in solving complex IT problems, which is definitely a private cloud, which is called as the Nimbus. So Sun scientists plan to smash two particle beams together in an attempt to recreate the Big Bang event to uncover the problem of many fundamental physics phenomena. Tens of thousands of scientists around the world are feeding the huge data sets and doing all kinds of research by themselves. Sun believes the cloud project will allow it, the Sun believes that the cloud project will allow it to deliver increased computing performance and offer better infrastructure services to its 10,000 researchers from 85 countries. At Sun, massive amounts of scientific data is processed and must be distributed to researchers in near real time. As a result, Sun's cloud infrastructure has to provide the capacity necessary to support production and analysis of more than 15 petabytes of data per year, processed by 60,000 CPU cores, allowing scientists to manage workloads themselves as opposed to a centralized IT management department at CERN's laboratory near Geneva. So Nimbus is a cloud OS that allows a user to securely provide context-specific information to a VM deployed on remote resources. Next thing is cloud mashups. A mashup is a web page or application that combines data, presentation, or functionality from two or more sources to create a new service. The main characteristics of the mashup are a combination of virtualization and aggregation. Figure below shows the concept of mashing up Google App Engine and AWS platforms. Essentially, one gets user input files from GAE, one gets user input files from the GAE and uses AWS infrastructure for MapReduce. To prove the effectiveness of mashups, the performance of MapReduce on mashup platform is experimented with scalable EC2 resources. The results of AWS GAE mashup experiments conducted at the University of Southern California. The mashup provider is crucial to link the two cloud platforms together. The mashup design leverages Google's web agility with the scaling power of AWS EC2. This mashup helps a user to write agile software on GAE and use the user inputs to perform parallel computing operations on AWS. There is another utilization of a cloud computing, which we call it as a cloudlets for mobile cloud computing. Mobile handsets face problems of limited CPU power, storage capacity, and network bandwidth on smartphones and tablet computers. Mobile devices cannot be used to handle large datasets. However, the distant cloud on the internet faces the WAN latency problem. Clouds have to solve this collision problem of too many clients logging into the cloud simultaneously. To solve this two-sided problem, cloudlets are being deployed at convenient sites, such as coffee shops, bookstores, similar to access points for Wi-Fi services for connecting to the internet. Widely deployed cloudlets enable distributed cloud computing and extended resource handling for these users. The idea is to use the cloudlet as a flexible gateway or portal to access the distant cloud. The cloudlet can be implemented on PCs, workstations, or low-cost servers. The major innovation lies in using VM-based flexibility to handle requests from different mobile devices. So the difference between cloudlet and the clouds is being mentioned on the few criterias like environment, state management, ownership, and network sharing, etc. So you can see over here there's a mobile device, there's a cloudlet. So first of all, mobile device will discover and negotiate the use of the cloudlet, because cloudlet is going to be charged. So basically, if it is a picker, it will charge more, and if it is not, then it will charge you less. So accordingly, it will discover and negotiate the use of cloudlet. Then private VM basically being used of the wherever the cloudlet is being implemented. So it has a preloaded base VM. So this base VM and the required overlay will be used to launch a new VM, and this new VM will execute basically whatever the data which is being required to be stored, or data which is required to be processed over here. And once the cloudlet is basically being created, the VM is being created, then the use of that VM will be done at the cloudlet side, and once it is being used, then basically uh, the mobile device will finish its use, and it will send the message to that the VM usage of VM is over. So it will discard the VM, and whatever the result is required, that is being sent back to the mobile device. So this is one of the best way of making use of local machines power and connectivity of the WAN through a mobile device. So another uh, so these are basically various I could say examples or cloud trends which are being used for ubiquitous computing. Like ubiquitous computing is nothing but computing from anywhere, anytime. So as per this, the NASA has provided the different cloud services, and the Nebula Cloud itself. So a platform which is now publicly being used, and by the scientists as well as the researchers. And CERN has also created its own Nimbus Cloud OS, which is basically can be used by anybody or deployed by any researcher who wants to do some research work on this kind of cloud OSs. Then we have seen the cloud mashups for agility and scalability. We have seen the usage of cloudlets in mobile cloud computing, and how the cloud and the cloudlets differs from each other. Basically, uh, it has only soft state, and the cloud has both hard as well as soft state. Basically, when we talk about state, means it basically uses the hardware which is available with the cloudlet, and then it comes the result is being used by this mobile device. So processing is done at the cloudlet, so it has both the states, that hard and soft state. Over here the cloudlet has only soft state. The cloudlet is being managed by itself, and it requires little to no professional attention, but cloud needs professionally administered, and 24 by 7 operator attention is needed. Like It can be a cloudlet can be a data center in a box at business premises, but cloud requires a machine room with power conditioning and cooling. So ownership of the cloudlet is decentralized ownership by local businesses. Cloud ownership is a centralized ownership either by big giants like Amazon, Yahoo, etc. The network which is required, the bandwidth which is to be used is basically of LAN, and for cloud the internet bandwidth is required. There are very few users at a time can share the cloudlet, wherein for the cloud there are more than thousands of users at a time can use this. Next point is performance of distributed systems and the cloud. So we have seen the high performance computing as well as high throughput computing. There is a difference between HTC and the HPC that we will be looking into. So HPC systems are advancing from petaflops performance in current supercomputers to exascale systems in the future. The HTC systems are primarily measured by the number of users tasks that can be processed per unit time. So that is nothing but a throughput. So HTC systems are measured from the perspective of the throughput. HPC systems are evaluated on the basis of attributes such as sustained speed, system efficiency, and availability. HTC systems are evaluated in terms of both throughput and the quality of service. There has been substantial investigation of clouds for research applications and infrastructure used for research in and use of cloud computing. In today's data-driven world, huge databases are generated from science in astronomy, genomics, natural languages, seismic modeling, among other applications, which leads to increasing demand for data-intensive scalable computing. So, if we need to see what is data-intensive scalable computing systems and how we can compare them with the supercomputers. So basically the supercomputers are essentially used in batch mode, and it is difficult to tune a supercomputer due to limited user control. So heavy data movement or IO activities exist when using supercomputers. It is rather challenging to optimize program execution on a supercomputer. The major advantage of supercomputers lies in their sustained raw speed if everything is put in order. Wherein DIC systems are HTC data center clusters, which have all the advantages of server clusters. DIC systems are much better in terms of satisfying a large number of simultaneous users with a high task throughput rate. Data centers can eliminate all single points of failure. Therefore, they are more reliable and highly available. DIC systems are more cost effective or time space efficient for small users. They can handle distributed computing applications using the cloud service model. There are some performance metrics which are being used for HPC or HTC systems. So for HPC performance has been defined over the years. The most popular metrics used are GFLOPS and teraflops in the past, petaflops on top systems now, and exaflops for the future. Parallel benchmarking programs are available to evaluate HPC systems in batch processing of a large scale problem. Well-known benchmark programs include the LinPack benchmark, NAS, Splash, and Park benchmark. HTC systems performance on business servers, clusters, data centers, and cloud systems is much more complex problem to evaluate because the systems are used by many clients simultaneously. This HTC system performance is attributed to many independent factors, Some of them are measurable and some of them are not measurable. The basic assumption is that many independent users may use the shared resources in the cloud or data centers simultaneously. The goal is to satisfy as many concurrent users as possible, even if each user program is a simple web service, social contact, or simple cloud storage. The performance models applied to evaluate MPPs, massively parallel processors, data center clusters, and virtualized clouds could be very difficult or different. Sorry. To fit the layered structure of the cloud computing paradigm, a good model should be able to cover all the layers of computing services. To assess quality of service in cloud services, the impacts on the top layer, that is software as a service layer, should remain transparent to the lower layer like PaaS and IaaS. IaaS. So five basic performance metrics are introduced, namely system throughput, multitasking scalability, availability measure, data security, and cost effectiveness. So in the system throughput of a distributed system or cloud platform measures the number of jobs that can be done per unit of time. If you consider execution time in which there are n independent jobs in a cloud platform and m accounts for the number of machine instances in a given system configuration, then the system throughput is, which is being denoted as a pi, is equal to n upon execution time by n number of independent jobs and m accounts for the number of machine instances. So it is a ratio of n by the effective execution time, where n is number of independent jobs and m is account for the number of machine instances. So system efficiency represents the effective utilization of all provisioned resources in a system. The parameters n and m in the expression vary with the low workload, system size, the parallel and distributed computing model applied. Next basic performance attribute is multitasking scalability. Multitasking implies the use of a system to handle many jobs simultaneously or concurrently. System services should be able to scale both horizontally across the machine or cluster size and vertically from applications to middleware, runtime and OS support and hardware. Horizontal scalability means to increase the cloud resources of the same type. For example, number of VM instances offers such a measure in a cloud. Vertical scalability means the increase in performance due to adding more resources along the service layers. We define the multitasking scalability denoted as a beta as follows. M is the number of machine instances and N is the total number of user jobs being processed. So in general, we have N is very large than M because N could be in millions and M can be only in hundreds. So the upper bound on the scalability is roughly indicated by the ratio of N is to M. So system availability refers to the percentage of time the system is up and running normally. This percentage reflects the effects of downtime after unexpected failures and scheduled maintenance for the software upgrades. The system availability is defined by the ratio of MTTF to the sum of MTTF and MTTR applies to all the systems.